Look at this photograph. A train, a machine of iron and steam, clings to the side of a mountain. Below it, a chasm of impossible depth. Around it, the jagged, unforgiving peaks of the Andes. This is the Trans-Andean Railway, celebrated as a monument to human ambition, a testament to the brute force of 19th-century will. The official story is one of heroism, a tale of brave engineers and thousands of laborers, armed with little more than dynamite, steam drills, and conviction, conquering one of the world's most formidable natural barriers. We are told they laid these tracks at over 10,000 feet, through solid rock, in the face of blizzards, landslides, and the crushing effects of altitude. A triumph of progress. But there is another story here. It is not written in the history books, but in the cold, hard language of physics and mathematics. It is a story told by the numbers. The weight of the steel. The consumption of the coal. The sheer energy required to move a mountain, one rock at a time. And when you examine that story, the official narrative begins to unravel. The logistics become a paradox. The timelines become an impossibility. What we are looking at is not a simple marvel of engineering. It is an anomaly. In this investigation, we will not speculate on fantasy. We will use the official records, the engineering specifications, and the fundamental laws of logistics to ask a simple question. Could the Trans-Andean Railway have actually been built the way they tell us it was? The evidence suggests an unsettling answer. The numbers do not work. The anomaly begins with what we can see with our own eyes. The railway line itself is a scar carved into a landscape that was never meant for human industry. The terrain is not merely difficult, it is actively hostile. We are talking about the Aconcagua mountain range, where peaks soar to over 20,000 feet. The railway navigates passes at an altitude of 3,200 meters, or more than 10,500 feet. At this height, the air is thin, temperatures can swing dozens of degrees in a single day, and sudden, violent snowstorms can bury everything in minutes. This is the environment in which the work was supposedly done. Now look at the work itself. We see long, elegant viaducts made of heavy iron, spanning deep gorges. Where did these massive, prefabricated sections of iron come from? The official account says they were forged in Europe, shipped to Argentina or Chile, and then hauled up the mountain. Hauled by what? The only transport available before the railway itself existed was the mule train. Imagine a narrow, treacherous mule track, barely wide enough for a single animal, winding its way up a 20-degree slope. Now imagine trying to move a multi-ton iron girder along that path. It's a visual contradiction. Then there are the tunnels. Not just a few, but dozens of them. The Summit Tunnel, the Caracoles, is a masterpiece of engineering, over 3 kilometers long, bored through solid granite. The alignment is perfect. Look at the archival photos of the men who supposedly built this. They hold hand-operated star drills and sledgehammers. They pose with small, primitive steam drills, machines that were notoriously inefficient and prone to breaking down, especially in the cold and thin air. The sheer scale of the excavation, the precision of the tunnel boring, seems to mock the tools we are shown. It feels like watching someone claim they carved a statue with a spoon. The visual disconnect is jarring. The result is industrial, precise, and massive. The supposed method is archaic, manual, and small scale. It doesn't fit. We see retaining walls built from enormous, expertly cut and placed stones, holding back entire mountainsides. Who were the masons with the skill and time to perform this kind of work in such conditions? Every element of the railway, from the gentle, consistent gradient of the track bed to the complex switchbacks and rack and pinion systems, screams of careful planning and immense power. Yet the story we are given is one of brute force and rudimentary tools. The landscape itself is the first witness against the official story. It tells you, silently, that something here is wrong. Something required to create this infrastructure is missing from the picture we have been given. To understand the true scale of the problem, we must move beyond what the railway looks like, and analyze what it would take to actually build it. Let us begin with the most fundamental challenge: logistics. Everything had to be brought to the construction site. Every rail, every sleeper, every spike, every bag of cement, every piece of machinery, every pound of food, and every lump of coal. The primary engine of logistics before the railway could support itself was the humble mule. A strong mule, on a good day, on a flat road, can carry around 100 kilograms. On a steep, high-altitude, unstable mountain path, that capacity drops significantly. Let's be generous and say 70 kilograms. Now, consider a single steel rail. A standard gauge rail from that era weighed about 30 kilograms per meter. For just 1 kilometer of track, you need 2,000 meters of rail. That's 60 metric tons, or 60,000 kilograms of steel. To transport the rails for just 1 kilometer of track would require over 850 mule journeys. That's for the rails alone. Add to that the thousands of wooden sleepers, the iron fish plates, the spikes, the bolts. The number of mule journeys for each kilometer of track quickly spirals into the thousands. This supply line wasn't moving along a highway. It was crawling along a dangerous, narrow path where a single misstep could send an animal and its precious cargo plunging into a ravine. This process had to be repeated, kilometer after kilometer. But the mules and their drivers don't run on air. They need food, water, and shelter. This creates a recursive logistical nightmare. A significant portion of your mule train is dedicated to carrying food for the other mules. The further you go up the mountain, the more inefficient the process becomes, until you reach a point where the supply train is almost entirely consumed with supplying itself. It is a mathematical black hole. Now, let's consider energy. The official story credits much of the rock cutting to steam-powered drills. A 19th century steam engine is a hungry beast. It requires two things in great quantity: water, which is scarce and often frozen at that altitude, and coal. Let's perform a simple calculation. A modest industrial steam engine of that era would consume at least 20 kilograms of coal per hour. If you have just 5 steam drills operating for a 10-hour workday, you are burning through 1,000 kilograms, a full metric ton, of coal every single day. That ton of coal must be mined, transported to the base of the mountain, and then hauled up the same treacherous mule paths. That's another 14 or 15 mule journeys every single day, just to keep a handful of drills running. And what of the men? The project supposedly employed thousands of laborers. These men were working at an altitude that severely impairs physical performance. They needed thousands of calories each day just to stay alive, let alone perform hard manual labor. This required a constant, massive influx of food, clothing, medical supplies, and building materials for their barracks. An entire moving city had to be supported, miles from any source of supplies, in one of the most inhospitable places on Earth. The construction of the camps alone would have been an enormous engineering feat. Where are the records for this? The detailed manifests? The supply chain ledgers? They are curiously absent. The narrative focuses on the heroic building of the railway, and conveniently ignores the impossible logistics that must have preceded it. The problem is simple. The very tools required to build the railway, the steam drills, the locomotives, depended on a supply chain that only a finished railway could realistically provide. You cannot use the solution to solve the problem of creating the solution. It is a paradox. It is a practical impossibility. When faced with such profound logistical contradictions, the logical step is to turn to the official records. One would expect to find meticulous project plans, detailed engineering reports, and exhaustive supply manifests from the companies that undertook this monumental task. One would expect the paper trail to explain how the impossible was made possible. Instead, what we find is a curious void. The official histories of the Trans-Andean Railway are rich in poetic language and heroic narrative, but they are critically poor in specific, verifiable data. They speak of indomitable spirit and conquering the mountain, but they do not provide the daily consumption logs for coal. They celebrate the genius of the chief engineers, but they do not include the weekly progress reports that detail the cubic meters of rock excavated versus the manpower expended. The language used is consistently that of mythology, not of engineering. This is a red flag. When the facts are strong, they are presented with clarity. When the facts are weak, they are shrouded in epic storytelling. We see this pattern repeated. The archives that do exist are often incomplete. Crucial periods of construction are glossed over with summary statements. Entire years are reduced to a few paragraphs about the immense difficulties faced, without explaining how those difficulties were overcome. When specific numbers are mentioned, they often conflict with other sources or seem implausible on their face. For instance, the number of laborers cited varies wildly, from a few thousand to over 10,000. The timelines for completing the most difficult sections, like the Summit Tunnel, suggest a rate of progress that, as we will later calculate, was simply not achievable with the stated technology. Furthermore, excuses for the missing data are common. We are told of fires in records offices, of documents lost to time, of archives destroyed in subsequent conflicts. While this is certainly plausible in isolation, it becomes a suspicious pattern when it happens repeatedly for the most critical pieces of evidence. The documents that would either confirm or deny the logistical feasibility, the supply chain ledgers, the fuel consumption reports, the detailed payrolls, are the very ones that seem to be systematically missing. What we are left with is a curated story. A template. It's a narrative structure you can find applied to dozens of other massive 19th century construction projects. A visionary leader, an impossible challenge, heroic and nameless laborers, and a triumphant completion against all odds, with the messy logistical details conveniently lost to history. This is not an explanation. It is a story designed to preempt questioning. It asks for faith in the spirit of the age rather than providing evidence for the reality of the achievement. The failure of the official story is not that it is wrong, but that it is fundamentally incomplete. It presents a conclusion, the finished railway, without showing the logical steps required to reach it. It is an answer without an equation. And in the world of engineering and physics, an answer without a verifiable equation is, at best, an unsubstantiated claim. The Trans-Andean Railway does not exist in a vacuum. If it were a single, isolated anomaly, it could perhaps be dismissed as a unique confluence of luck, genius, and heroic effort. But it is not an isolated case. It is part of a global pattern of seemingly impossible mega-constructions that appeared during the 19th and early 20th centuries, all of which share the same narrative flaws. Let us travel to Europe, to the Swiss Alps. The Gotthard Railway, constructed between 1871 and 1881. Its centerpiece is the Gotthard Tunnel, a staggering 15 kilometers long, bored through the heart of a mountain range. The official story is that it was built using advanced compressed air rock drills and dynamite. But again, we must ask the logistical questions. The machinery for the drills was powered by water turbines, a clever solution, but the infrastructure to build the dams, penstocks, and turbine houses was a massive project in itself. The sheer volume of rock to be removed, over 1 million cubic meters, and the logistics of supporting thousands of workers in remote mountain valleys mirrors the Andean problem precisely. The official account speaks of high mortality and labor strikes, but it glosses over the fundamental challenge of supplying the energy and materials required for such a rapid pace of construction. The story is the same, an impossible result, attributed to a new technology, with the supporting logistics left unexplained. Now let us go back further, to the Semmering Railway in Austria, completed in 1854. This was one of the very first standard gauge mountain railways ever built. It features 16 major viaducts and 15 tunnels, carved out of the mountainside with technology that was even more primitive. We are talking black powder, not dynamite. We are talking primarily manual labor. Look at the precision of the stonework on the viaducts. Look at the perfect curvature of the arches. All of this was supposedly achieved in just 6 years, in a mountainous region with harsh winters. The official narrative celebrates its designer, Carl von Gege, as a singular genius. But it never adequately explains how tens of thousands of tons of stone were quarried, dressed with such precision, and lifted into place using rudimentary cranes and manpower. The material logistics are, once again, the weak point of the story. Let's look at another continent. British India, the Darjeeling Himalayan Railway, climbing over 7,000 feet. Or the mountain railways of Sri Lanka. In all cases, we find the same pattern. Extreme terrain, supposedly primitive technology, an impossibly fast construction timeline, and a historical record that emphasizes the grand vision of the colonial engineers while remaining conspicuously silent on the practical, mathematical details of the supply chain. The recurring motif is one of discovery and completion, not of creation from scratch. It is as if these projects were about finishing a job, not starting one. The story template is identical: a formidable natural barrier, a brilliant engineer, an army of anonymous laborers, and a triumph that defies a logical analysis of the available resources. This global pattern suggests we are not looking at a series of independent miracles of engineering. We are looking at a single, misunderstood phenomenon. The Trans-Andean Railway is not the exception. It is a prime example of a story we have been told, time and time again, all over the world. A story that, upon closer inspection, does not hold together. let us set aside the heroic narratives and focus on the unyielding reality of numbers. Mathematics is the universal language of engineering. It does not care for ambition or spirit. It cares only for what is possible. First, let's revisit the transport of steel rails. A 1-meter section of 75-pound rail, a common standard for the era, weighs approximately 37 kilograms. The Trans-Andean Railway's most famous section, from Mendoza to Los Andes, is about 250 kilometers long. For a single track, this requires 500 kilometers of rail. The total weight of the rails alone is 18,500 metric tons. That is 18.5 million kilograms. Using our generous estimate of a mule carrying 70 kilograms on a mountain path, the transport of the rails alone would have required more than 264,000 individual mule journeys. This number does not include the hundreds of thousands of sleepers, the tons of spikes and fish plates, or any other construction material. It is a staggering figure, representing years of continuous, perfectly coordinated effort before a single section of track could even be laid. Now, let's analyze the tunnel excavation. The summit tunnel, Tunnel de la Cumbre, is 3.2 kilometers long. Let's assume a modest cross-section of 15 square meters. This gives us a total excavation volume of 48,000 cubic meters of solid rock. The official timeline for this section of the railway implies this tunnel was bored in a few years. Let's say, generously, 4 years of work. That's 1,460 days. This means that, on average, the workers had to excavate 33 cubic meters of solid granite every single day. A cubic meter of granite weighs about 2.7 tons. So they had to remove nearly 90 tons of rock, every day, from a confined tunnel, using inefficient steam drills and hand tools. This brings us to the most critical number: labor productivity. At high altitude, over 10,000 feet, human physical work capacity is reduced by at least 25% due to hypoxia. So, a workforce of 4,000 men on the mountain is equivalent to a workforce of only 3,000 at sea level. Historical data on manual rock excavation from that era suggests that one man, in a 10-hour day, could remove perhaps 1/10 of a cubic meter of hard rock. Being generous again, let's double that to account for rudimentary machinery. Even with a large workforce inside the tunnel, it's difficult to imagine how they could achieve a rate of 33 cubic meters per day. The numbers suggest the project would take decades, not years. The logic leads to a breaking point. The energy required to remove the mountain was immense. That energy had to be supplied in the form of coal and food. The transport of that fuel and food required its own massive expenditure of energy, via the mule trains. The system consumes itself. The math simply fails. The official narrative requires us to believe that all of these logistical and physical barriers were overcome simultaneously. But the numbers tell a different story. They tell us that the project, as described, was not just difficult. It was mathematically unsustainable. We are faced with a deep contradiction. The physical evidence of the railway exists. The logistical impossibility of its claimed construction also exists. When the official explanation fails to account for the facts, we must consider alternative hypotheses. This does not mean we must turn to fantasy or speculation about lost technologies or ancient aliens. It means we must look for a more logical, more parsimonious explanation that fits the available data. Let us propose a controlled hypothesis. The great work of the 19th century project was not one of construction from nothing, but one of reconstruction and completion. Let's imagine that the engineers, Clark and his contemporaries, did not arrive to face a pristine, untouched mountain range. What if they found something already there? Not a railway, of course, but the groundwork. A pre-existing, expertly graded path. A series of rough-hewn, but strategically placed, tunnels. The basic, foundational earthworks and rock cutting already completed by an unknown predecessor. In this scenario, the 19th century project becomes an entirely different undertaking. Their task was not to conquer the mountain, but to build upon a conquest that had already occurred. Their job was to widen existing tunnels, to stabilize slopes, to lay the sleepers and the steel rails, and to construct the iron bridges over chasms where, perhaps, more primitive structures once stood. This hypothesis elegantly resolves the major impossibilities. The problem of material transport for the initial, most difficult phase of construction is largely eliminated. The massive steam drills and earth-moving equipment were not needed to do the primary excavation, only to finish the job. The astronomical amount of coal needed to power this initial phase was never required. The timeline suddenly becomes plausible. Laying track, finishing tunnels, and building viaducts on a pre-existing roadbed is a far more manageable task than creating that roadbed from solid rock at 10,000 feet. The heroic narratives of conquering the Andes can be reinterpreted. Perhaps they were not literal descriptions of the work, but a form of propaganda, taking credit for a much larger, older achievement. This would explain the lack of detailed logistical records for the early phases of construction, because there were none. The most difficult work had already been done. Who could have performed this initial work? The hypothesis does not need to answer this question. To name a specific civilization or group would be pure speculation. The important point is not who, but what. The evidence on the ground suggests a level of engineering and logistical capability that is not accounted for in our accepted history of the region. The 19th century builders may have been just as mystified as we are. They found a path, and they used it. This controlled hypothesis is superior to the official story for one simple reason: it fits the facts. It respects the laws of physics and logistics. It explains the visual anomalies, the mathematical paradoxes, and the missing records. It is a disquieting thought, but it is a rational one. We are not looking at a single-layer story of 19th century triumph, but at a multi-layered history, where the most recent layer has obscured the deeper, more profound one that lies beneath. We are left with a fundamental conflict. On one hand, we have the story we are told. A story of progress, of humanity's triumph over nature, built with steam, sweat, and dynamite. It is a reassuring story. It reinforces our belief in a linear, upward path of technological achievement. On the other hand, we have the cold, hard reality of the numbers. The physics of the Andes. The logistics that defy the story at every turn. The mathematics of the mule train and the steam drill present a paradox that cannot be easily dismissed. The Trans-Andean Railway should not exist, at least not in the way it was supposedly created. The energy required to build the path was dependent on a path that did not yet exist. The official story is not just a story, it is a paradox. This investigation does not claim to have the final answer. We do not know who carved the initial path, or when. But the evidence strongly suggests that the official narrative is, at best, a simplification and at worst, a fiction designed to cover a gap in our understanding of the past. The questions raised by this single railway line in the Andes echo across the globe, bouncing off countless other structures that defy their own creation myths. We are encouraged to look at these marvels and feel pride in our ancestors' achievements. But perhaps we should look closer. Perhaps we should ask the simple, practical questions. How much did it weigh? How was it moved? How was it powered? When you begin to ask these questions, the world starts to look very different. The landscape is filled with mysteries that hide in plain sight. All that is required to see them is to stop accepting the story and start doing the math. If you believe these questions are worth asking, there is more to investigate. The patterns are everywhere, once you learn how to see them. Look closer.